5 minutes during third period.
Okay.
It is.
So Green's theorem is what we're going to focus on today.
Who's Green?
Math. Well, actually, his story is unusual. He's I forget I want to say he was like a self-taught mathematician who was the son of a baker. I want to say. I don't remember the story, but like he had an early death, unfortunately, and all I know is that this is one of his big works, and it applies to a lot of physics, obviously. And at the time that he published all his findings for this, there was not that much press or that much anything, so it was really not all that big of a deal. But then after he died, of course, and like, oh my gosh, look at all this work.
So mathematicians are like artists.
Oh yes,
Where
absolutely.
did he live?
I don't know. I forget where he was from.
No, when?
Oh, when?
Like what decade / era / century?
It's probably, maybe you should.
You know, I bet if you Google it, you could find out faster than I can remember.
I'm guessing 70s.
It's probably like English. Does this provide any history?
Yeah, it does.
It might.
Yeah,
Okay.
that's right. I can't recall when he was born.
English math, 1793 to 1841.
I was going to say 18th century, so I sort of would have been right. Okay.
It's not very-
Let R be a simply connected plane region. Is it still weird? Let's try this again. Is that better? Yeah. Whose boundary is a simple closed piecewise smooth curve.
We're just going to keep adding adjectives to the verb.
Yes. Oriented counterclockwise. This is important here. That means so if this is R, that means that we travel around the region along the path in a counterclockwise fashion, so that the region on the interior is always on the left-hand side. That's what we call positive orientation. So if you imagine running around a track or driving around a racetrack, that would be the natural way to do it. So that's a good way to remember it. Positive orientation, or normal for us, would be region on the left as we go around. Okay? So that's all that means. Now, if f of xy and g of xy are continuous and have continuous first partials, on some open set containing R, then the line integral of f of xy dx plus g of xy dy, which, by the way, is one way to evaluate f dot dr, right? So don't forget that. And this is now where we start to bring in things that we learned before. So this is kind of a very nice theorem for us. We could perform this computation by doing the double integral over whatever that region R is that's contained within the curve of partial g partial x minus partial f partial y dA. Okay, so this is Green's theorem. obviously all the description here, those are the conditions that we need to have in place. This is the bulk of what you need to remember. Closed path, work integral, you can do a double integral to figure out the value of the integral. Okay?
Wait, why does it matter that it's oriented counterclockwise? Because if you do work,
Is it this positive versus negative?
This is not necessarily a conservative,
Oh.
right? In fact, if it were conservative, we already know what the work would be, right? What would it be?
0.
Yeah, because if we're completing the loop, it's not going to matter how we do it. You're right. But this is not necessarily for a conservative field. So the orientation would change it. If any, I mean, and it's going to do exactly what it did before. If we were to go around the other direction, then it's just going to switch the sign of our integral. Okay, so that would get reversed. And actually, we're going to prove this. So you're going to see how the connection is made here. Okay, so pretty big results. So we are going to spend the time to understand how this actually links together. So here's what we'll do. We are going to kind of have the same picture that we have up here. And just to keep things simple, we're going to argue that our region can be considered either a type 1 or a type 2 region, like we talked about last unit. So if that's the case, then we can say here on the lower end of things we have g1 of x as the lower bound, and let's say for the top part of the region we would say g2 of x is the top bound. Okay, or if we just switched our perspective, we can do the same thing but from the other direction. So now we're between C and D, and then our left boundary we could say is h1 of y, and our right boundary would be h2 of y. And again, we're keeping the orientation as described above. Okay, so consider this region. All right. I think it's pretty clear that in order to get this to match up, we need to show that the line integral of f of xy dx, well, that's going to become the double integral of negative partial f partial y dA. I mean, that's the only way that this would make sense. And then obviously g of xy dy, that would have to give us the other portion of the double integral on the right hand side. Okay, so let me actually label these. So we need to prove these two statements. Okay, so basically our proof is going to look something like this. We're going to spend a considerable amount of time proving the first one, and then just argue that the second one's going to follow by similarity, because it's going to be the same argument. Okay. So now, to prove the first statement, we'll let C1 and C2 be the boundary curves. Like so. So we'll put C1 as the bottom curve and C2 as the top curve.
Why not just keep using the G2 and G1?
Well, we have to bring that in somehow, because right now what we're going to do is actually split this up into two separate line integrals. So we're going to evaluate the line integral along C1 and then along C2. Okay. So, am I still? Yes, still on the screen. Okay. So then the line integral of f of xy dx will be exactly what I just said. If we split it up like this, we're going to split it up into two line integrals along each path.
They have been not the same as
This should be a lowercase, yeah. And now, to keep things with the same bounds, okay, so basically to integrate in the same direction, we're going to reverse the direction of the integral here. So here we're going to integrate from left to right, and obviously if I'm going along C2, I'm integrating from right to left, so to avoid that, I'm just going to reverse the direction. So then this would become minus the integral, and then now we put a little negative sign in front of the C2 to indicate that the direction has been reversed. Okay. And now when we integrate these line integrals, we need some sort of parameterization for them. Okay, so what we can do is a standard parameterization. So for C1, if we let x equal t, and now here's where we bring in the g1 and the g2. If we let y equal g1 of t, and we do the same for C2, x equals t, but now y would be g2 of t, and now our bounds, we're going to go back to this first picture here. Our bounds for t, since t is x, is just going to be from a to b. So a would be less than or equal to t, which is less than or equal to b. So now if I plug in these values, here's where we're at currently. We know that the line integral of f of x y dx, which used to be these two things here, are now going to become the integral from a to b, plug in the parameterization, so x is going to be t, so that's f of t, and then y is now g1 of t. Oh, whoops, that should, you know what, let me rewrite that. T comma g1 of t dt. Since x and t are the same, that means dx and dt will also be the same. So everything is now in terms of t for this integral, and this one will be minus the integral from a to b of the same thing, but just g2 now. Okay, so now our job is basically to take the stuff that's in the blue there and try to somehow explain where this double integral now can get substituted for it. So one thing that we can do is kind of rearrange things in terms of one integral, and what I'll do is take out a negative. I mean, why not? We needed a negative on our right side of the equation there, so it makes sense to do that. Okay, so if we take the negative out, now I'm going to put f of t comma g2 of t first, minus f of t comma g1 of t, and now that's with respect to t, so dt. Well, doesn't this look suspiciously like an integral was evaluated in here? When you plug in upper bound, lower bound? So let's write what that had to have been. That means we had some function, f of t comma y, and y was evaluated from what? G1 to G2. So G1 of t and then G2 of t dt. Almost there. Now, where did this come from? So before we plug in the bounds, right, we had to integrate some function from G1 to G2, and it was integrated with respect to y, right? So that means in here we had something like partial f partial y dy. So now this part turns into this. And we basically have what we need. Keeping in mind that t and x are one and the same, we could rewrite this as the negative integral from a to b, and from g1 of x to g2 of x of partial f partial y dy, and again, since dt and dx are the same, we can replace that back in terms of dx. And now this would be exactly the double integral over the region R of partial f partial y dA, as we needed to show. Okay? Do you have to do that? I don't know. Be a good one to know. Similarly, we're going to say that the line integral of g of xy dy is the double integral over the region R of partial g partial x dA. So this proves Green's theorem, which is a pretty awesome result because now you can tie in some double integrals to these line integrals that we've been working on. Okay, so we'll do a couple of examples. Yeah, we got some time. All right. So let's say we have the line integral of y cubed dx. Oh, is it not open? Plus x cubed plus 3x y squared dy. And let's say here's our path. Y equals x will be the top part. And let's say this is y equals x cubed. And let's say the orientation is counterclockwise. So this is C. So here's what we want to figure out. Here's our path. Okay. Now I should also say, just because this is important for you to make the connection, that this is also equal to f dot dr, where our vector field is what? Good. So just because it's not in that format doesn't mean that we're not integrating over a vector field. I mean, so you got to be able to make sure that you see the connection between the two. whether it's in this form or that form. This is essentially what we're doing. Okay, so it's not hard to figure out. I would definitely suggest using Green's theorem. Why?
So he's got separate GX and
What's the big condition that we need?
Yeah, it is counterclockwise.
Yes, but more importantly, it's a closed path, right? Anytime it's a closed path, we can use Green's theorem. Okay, so to set up the integral, all we need to do is partial g partial x minus partial f partial y. Let's do dy dx over. Actually, we can plug in the bounds, I guess. The lower bound for y would be x cubed. The upper bound would be x. Thanks. Okay. And then for x, what would the bounds be? 0 to 1. So then all we have left to do, remember that this is f of xy right here, right? This is g. Let's plug everything in. Partial g partial x would be what? Minus partial f partial y, which would be 3y squared. Well, that's nice. So that's just going to be 3x squared. Whoops. Dy dx. So that becomes 3x squared. Well, I guess I don't want this bound in there anymore. Sorry. 3x squared times y from y equals x cubed to y equals x dy. So that's from 0 to 1. And if I plug in the bounds, we're going to get 3x cubed minus 3x to the 5th dx. Sorry, thank you. Trying to squeeze it in on this page. So then the integral for that, that's 3/4 x to the 4 minus 3/6, so 1/2 x to the 6th from 0 to 1, which gives us 3/4 minus 1/2, so that's 1/4.
So like those problems that we did before with like the triangles.
Oh, you can totally use
You can
Green's.
do this, right?
Yes.
You don't have to go and do each part separately
Absolutely.
and then add them up like we did before.
Absolutely.
Do we ever have to do that again?
If the directions don't specify how to do it, you can do it however you want.
Awesome.
Okay? All right. All right, so in addition, let's talk about some common notation before we do the next example. So if we have a closed path, sometimes you'll see this notation.
It's the thing with the circle.
That's what that means. So then a shorter, more concise way of saying Green's theorem without all those conditions written out, if you just have the symbol, we know we have a closed path. And then we know that we could say that's double integral partial g partial x minus partial f partial y dA. Okay, so if you see that little circle on the integral, that means we're integrating over a closed path. Sometimes you'll even see a direction specified on the integral sign. So if you see something like this, I don't know where they usually put it. Actually, they probably put it on the left. So if you see a little circle with the arrow indicating the direction, now you know which way it's oriented, positively or the opposite of that. Yes? Yep. Mm-hmm. Okay. I guess we don't need to do that example. We already talked about this, so we can just write it down. If f is conservative, then what is the value of f dot dr over a closed path? 0. Okay, we know that because it's conservative. You could also argue that partial g partial x has to equal partial f partial y if it's conservative, right? So then we're basically integrating 0 dA. Okay, but we already knew that. Okay, here's another application of Green's theorem. Area. We talked about last unit. If we were to do a double integral, that's the integral of just dA. Okay. Now, you could also do the line integral of x dy, or the line integral of negative y dx. Or if you wanted to, you can add these two and take half of the sum. Sometimes it makes the calculations a little nicer. Okay, now if you're not seeing where the connection is to this, you could set g of x, y equal to x, and f of x, y equal to 0. So then if g of x, y is equal to x, in the calculation here, what would partial g partial x be? So then we're left, and then partial f partial y would be 0. So then we're left with just 1 dA. Okay, so I mean that's where these are coming from. And then you can argue the same thing here. So if we set partial f partial y to negative y, we also get 1 dA. Okay. Why are we allowed to? Well, because basically if we split up, if we ignore this, this first part represents area, but so does the second part, right? Now the reason that you might want to do this is sometimes this cleans up the calculation. So sometimes it's useful to add everything up because things might cancel out and make the calculation a little nicer. But then you'd have to take half of that. Exactly. So that's why the half is there. So actually let's do a quick example using that application. Use a line integral to find the area of the ellipse x squared over a squared plus y squared over b squared equal to 1. Well, that's going to be the idea here eventually, yeah. So if we're going to use a line integral, let's say I did x dy to start. Let's see if that gives us a pretty decent calculation to work with. If I integrated x dy, let's do a parameterization here. So thinking of the ellipse, this has to be A, this has to be B, right? What would x equal and y equal here? It's a sine and cosine thing, yeah. Yeah, usually it's A cosine theta, or in this case we're going to use t. And then y would be B sine t. That's the standard parameterization for an ellipse. If this were a circle, then obviously A and B would be the same. Okay? Now, using that parameterization, and by the way, what's t here? From what to what? What does theta, or t in this case, have to be in order to get our whole ellipse? 0 to 2 pi. Okay, so now I'm going to rewrite this integral from 0 to 2 pi. I'm going to plug in x, which is A cosine t.
Wait, do you have to do the simple?
Well, no, because now I'm evaluating it. So I'm actually plugging in, like once you plug in the bounds for the integral, you don't have to do the circle thing.
Does the circle thing have an official name, or we just call it the circle?
This is just the line integral over a closed path. But I'm not going to call it the circle thing. That's like when I teach trig for the first time and my students are all leaving pre-calc talking about sins and tans and causes and pitchforks and all these Greek letters that they don't know. Psi.
Trends.
What is
We've never used that one. Wait,
It's just a Greek letter. I like to introduce them to the Greek alphabet because they've never seen it before. So, you know. Anyway, continuing the calculation. A cosine t dy. What would dy be?
Or b cosine t.
B cosine t dt, right? Well, that's not too bad. Let's see. We can pull out the a and the b, since those are constants. Cosine squared t is now what's left. And if you did your homework last unit, cosine squared we can write as,
Yeah, 1/2 plus 1/2 cosine 2t.
good. So this is not a hard calculation at all. So we're going to stick with just x dy, and I'm off the screen again, sorry. So we have AB times 1/2 t plus 1/4 sine 2t from t equals 0 to 2 pi. If I plug in the bounds, the sine term would cancel out either way. So really all I have to worry about is this 1/2 times t, so that's going to give us pi a b.
Oh, that is the formula.
Well, yes, we're not going to get anything different. Okay. So we have Green's theorem for closed paths. You can calculate work with that if it's a closed path. You can calculate areas using line integral. And then let's wrap things up briefly by just talking about multiply connected regions. We won't have time to go through a whole example, but we can at least talk about what you would need to do. Okay. So multiply connected regions means we have some closed path. Let's say this is C1. But then within this region, there is a hole or some other path that creates the hole. So let's say this is C2. Let's say the orientation is this way. Okay. So let's say this is our scenario. Now, we want to try to use Green's theorem. The first path, so if we go along C1, this is going to be set up exactly the way we discussed earlier. So we're going to have line integral of f of xy dx plus g of xy dy, C1, and closed path. So that would calculate if we're on this path on the outside. But now if we want to traverse both paths, then at some point, we talked a little bit about this yesterday, and it's really arbitrary, it's not going to matter. So let's say I start here, and then once I get over to this point, I decide I want to get to C2 and take care of going around C2 once. So then I follow the orientation, I come back to where I started. So now C2 is taken care of. But then, now what do I do to get back to where I left off with C1? You got to go back along that same path. So this orange path will contribute nothing to the integral. Does that make sense? Because we're going one way, figuring out this other integral, which we'll write down in a minute, but then to get back, those two parts would cancel out because of the opposite direction. Okay? So the only trick that we have to do here, let me put this one in blue, is when we do this integral, we're just going to have to reverse the orientation. That's all. Okay? So for this one, we reverse the orientation. So we can still set up Green's theorem and do the calculation. The only thing that's going to happen is when we set up our double integral for this blue path, we're just going to switch the sign. That's all that reversing the orientation is going to do. Because in order to use Green's theorem, we want counterclockwise orientation, right? And right now, if you look at the way path C2 is depicted, we're going around clockwise with everything on our right-hand side. Okay, so if we switch the direction, that's going to switch our double integral. Okay? Let's see, is there anything else I want to do? I think that's good. So, I mean, we could even clarify. This would be double integral of partial g partial x minus partial f partial y dA. And when you reverse the orientation, let's call this sub-region r, I don't know, little r? Sure, why not? So this would be little r, but now we're going to switch the integrand, so that's going to be partial f partial y minus partial g partial x.
Wait, is this just for this scenario? Like
Yes.
if they were both going the same way,
If they were both going the same way, then you wouldn't have to worry about reversing the direction. Yeah. So I mean, and this reversing the direction, the orientation, that could happen on any given problem. So I mean, it's not typical. You know, once we establish this is positive orientation, we're mostly going to be working in that mode. But occasionally you might see a problem where things are backwards, and if that's the case, then this is what you would do to account for that. Okay? All right. See you guys tomorrow.